Good day, ma'am. I'm Joseph D. Machado Jr. from BCE 1B. Lecture 1, Heat Transfer. Problem set. 1. Example 1.10, page 39 to 40. A polystyrene foam icebox has a total area of 0.950 m square and walls with an average thickness of 250 cm. The box contains ice, water, and canned beverages at 0 degrees Celsius. The inside of the box is kept cold by melting ice. How much ice melts in one day if the ice box is kept in the trunk of a car at 35.0 degrees Celsius? Given K is equals to 0.0110 watts per meter degrees Celsius for the polystyrene foam or thermal conductivity of the material, and surface area in contact is 0.950 m squared, and D or thickness of the surface is equals to 2.50 centimeter is equivalent to 0.0250 meter, and temperature of the holder is 0 degrees Celsius, and the temperature of the hot surface is 35.0 degrees Celsius. Then time, 1 day is convert na to ang 1 day is equals to 24 hours. Then 1 hour is equals to 60 minutes, and 1 minute is equals to 60 seconds. So atong i-cancel out ang kini hours, day, 1 day, 1 hours, and 1 minute. So is 60 seconds. So ang equivalent is 84,400 seconds. Solution. So this is the equation. P is equals to dq over dt is equals to Ka times TH is temperature of hotter surface minus temperature of the colder over thickness of the surface. So 0.010 watts per m degrees Celsius is the thermal conductivity of the material, times 0.950 m squared is the surface area in contact, times so kinang Ka man siya, then times temperature of colder is hot surface 35.0 degrees Celsius minus 0 degrees Celsius sa iyang temperature of the colder. Then we divide 0.0250 meter tong thickness of the surface, then we're going to substitute. So this is the answer, 13.3 watts. Then multiplying the rate of heat transfer by the time, 1 day is equals to 86,400 seconds. We obtain Q is equals to PT is equals to 13.3 watts times 86,400 seconds. So this is the answer, 1.15 times 10 6 a raised to the power of 6 joules. Then we set this equal to the heat transferred to melt the ice. Q is equal to MLF, and solve for the mass meter. So this is the equation. Then 1.15 times 10 raised to the power of 6 joules over 334 times 10 raised to the power of 3 joules per kilogram. So atong i-cross out ang joules. So ang mabilin is 3.44 kilogram. So is this amount of ice melts in one day when it kept in the trunk of a car at 35 degrees Celsius. Problem set number 2, example 1.11, page 41 to 43. Two conductors end to end. Question: a steel rod and aluminum rod, each of diameter 1.00 and length 25.0 cm, are welded end to end. One end of the steel rod is placed in a large tank of boiling water at 100 degrees Celsius, while the far end of the aluminum rod is placed in a large tank of water at 20 degrees Celsius. The rods are insulated so that no heat escapes from their surfaces. What is the temperature at the joint, and what is the rate of heat conduction through this composite rod? Solution: convert the given to SI units. Length of each rod is 0.25 meter, and cross-sectional area of each rod is 7.85 times 10 raised to the power of negative 5 meters square. Thermal conductivity of aluminum is 220 watts per meter degrees Celsius. Thermal conductivity of steel 80 watts per meter degrees Celsius. Temperature at the hot end is 100 degrees Celsius. Temperature at the cold end is 20 degrees Celsius. Still is this as a equation. Thermal conductivity of the steel is 80 watts per meter degrees Celsius times cross-sectional area of each rod is 7.85 times 10 raised to the power of negative 5 m square times temperature at the hot end 100 degrees Celsius minus T, or T is 100 degrees Celsius, divided by 0.25 meter. So we're going to substitute. So this is the answer of P steel, 0.0251 watts per degree Celsius times 100 degrees Celsius minus T. Then aluminum P is equals to thermal conductivity of aluminum is 220 watts per meter degrees Celsius times thermal cross-sectional area of each rod is 7.85 times 10 raised to the power of negative 5 m squared times T minus 20 degrees Celsius over divided by 0.25 meter. So answer of aluminum P is 0.0691 watts per degree Celsius times T minus 23 degrees Celsius. Set the two rates equal and solve for the unknown temperature. 0.0691 watts degrees Celsius multiplied by T minus 20 degrees Celsius is equals to 0.0251 watts degrees Celsius multiplied by 100 degrees Celsius minus T. So the answer of T, or temperature is equals to 41.3 degrees Celsius. So we're going to calculate the either rate. Still P is equals to 0.0251 watts per degree Celsius multiplied by 100 degrees Celsius minus 41.3 degrees Celsius. So the answer is 1.47 watts is the rate of heat conduction for steel. Problem set number 3, example 1.12, calculating the flow of mass during convection. Question: the average person produces heat at the rate of about 120 watts when at rest. At what rate must evaporate from the body to get rid of all this energy? For simplicity, we assume this evaporation occurs when a person is sitting in the shade and surrounding temperatures are the same as skin temperature, eliminating heat transfer by other methods. Strategy is needed for this phase change. Heat energy is equals to mass times evaporation, evaporation. Thus the energy loss per unit time is heat energy over time is equals to mass times L evaporation over time is equals to 120 watts is equals to 120 joules per second. We divide both sides of the equation by LV or evaporation to find that the mass evaporated per unit time is mass over time is equals to 120 joules per second over LV. Solution: insert the value of the latent heat from table 1.4. L evaporation is equals to 2,430 kilojoules per kilogram is equals to 2,430 joule per gram. Mass times mass over time is equals to 120 joules per second over 2,430 joules per gram is equals to 0.0494 gram per seconds is equals to 2.96 gram per minute of the mass over time. Problem set number 4, example 1.13, page 49 to 50. Calculating the net heat transfer of a person. Question: what is the rate of heat transfer by radiation of an unclothed person standing in a dark room whose ambient temperature is 22.0 degrees Celsius? The person has a normal skin temperature of 33.0 degrees Celsius and a surface area of 1.53 meters square. The emissivity is 0.97 in the infrared, the part of the spectrum where the radiation takes place. Solution: insert the temperature values T sub 2 or temperature of the environment in Kelvin is equals to 295 Kelvin and T sub 1 or temperature of the object in Kelvin is equals to 306 Kelvin, so that heat energy all over time is equals to Q times E surface area in contact or surface area of the object multiplied temperature of the environment raised to the power of 4 minus temperature of the object in Kelvin raised to the power of 4 So gihatagan na siya mo siya ang Stefan Boltzmann law of radiation, or net rate of the heat transfer by radiation multiplied by is equals to 5.67 times 10 raised to the power of 8 joules per second times m squared times Kelvin raised to the power of 4 multiplied by 0.97. 97 is the emissivity multiplied by 1.50 meter square, and a surface of area bracket multiplied by 295 Kelvin times 4 ko pa to no? Minus times 306 Kelvin patong gyapon siya 306 Kelvin. So we're going to distributing, then is equals to negative 99 joules per second, then final is 900 negative 99 watts. That's all. Thank you.